all to the session of Laplace transformation. Myself, Lalitha Ramachandran, Assistant Professor, Department of Mathematics, RK Engineering College. In this video, we would get ourselves introduced to the concept of Laplace transformation, definition of Laplace transformation, condition for existence of Laplace transformation, and Laplace transformation of some elementary functions. To get started up with the introduction to Laplace transformation, Laplace transformation is an integral transform that provides a powerful means to solve linear ordinary differential equations in the time domain by converting the linear differential equations with initial conditions into algebraic equations. Laplace transformation belongs to a general area of mathematics called operational calculus, which focuses on the analysis of linear systems. The process of changing from operations of calculus to algebraic operations on transforms is known as operational calculus. The name is due to the French mathematician Simon Laplace, who used these transforms while developing the theory of probability. Laplace transform converts continuous time signals into frequency domain. This capability of transform to convert time domain to frequency domain makes it very useful and makes many applications in science and technology too. The Laplace transforms can be used to solve the differential equations, partial differential equations, and integral equations very easily. Solving these complex equations becomes so easy with Laplace transform because this Laplace transform converts the complex equations to algebraic equations that can be easily solved. Laplace transform can also be used to solve initial value problems and to convert convolution into multiplication. Laplace transform are also useful in the field of physics, electrical engineering, control engineering, optics, and signal processing. So now you can understand how powerful and versatile tool the Laplace transformation is. It's time to see the formal definition of Laplace transformation. If f of t is a well-defined piecewise continuous function of t for t to be greater than 0, and if the definite integral 0 to infinity e power minus st f of t dt exists, then the Laplace transform is defined as Laplace of the function f of t is equal to integral 0 to infinity e power minus st f of t dt for s to be greater than 0. Symbolically, it is represented as Laplace of the function f of t is equal to capital F of s, or Laplace of the function y of t is equal to capital Y of s. The equation 1 could also define the inverse Laplace transformation. Symbolically, to represent Laplace inverse of capital F of s is equal to the function f of t, or Laplace inverse of capital Y of s is equal to the function y of t, where L is called the Laplace transform operator, f of t is called inverse Laplace transform and also the object function of t, capital F of s is called the resultant image function, and the parameter s is real or complex number. Here we assume s to be a real number. Let us get to know the condition for existence of Laplace transform. The Laplace transform of f of t exists if f of t is of exponential order. It means that if there exist constants m and a such that modulus of f of t is less than or equal to m into e power at for all t greater than 0. Here, the parameter should be large enough to make the integral convergent, and also the condition for existence of capital F of s is sufficient but not necessary. Geometrically, it means that the graph of f of t does not grow faster than the graph of exponential function m into e power at for t to be greater than or equal to 0. Now, we apply the definition of Laplace transformation to some elementary functions. First, let us find out the Laplace transformation of the function f of t to be a constant. We know that the Laplace transform is defined as Laplace of function f of t is equal to integral 0 to infinity e power minus st f of t dt. Here in the question, the function f of t is a constant, say c. In place of f of t, we substitute the constant c. L of c is equal to integral 0 to infinity e power minus st c dt. Since c is independent of t, we write it as c into integral 0 to infinity e power minus st dt. Integral of e power minus st could be written as e power minus st divided by minus s by integrating it with respect to t and apply the limit t which varies from 0 to infinity. Next, we apply the upper limit minus lower limit and we get c divided by minus s into e power minus infinity minus e power 0. We very well know that e power 0 takes the value 1 and e power minus infinity gives 0. So, we get c divided by minus s into 0 minus 1. So, when simplified, we get c divided by s. Hence, we have proved that the Laplace transformation of the function f of t to be a constant is nothing but c divided by s. Now, in particular case, if the function f of t was 1, then the Laplace transform of the function f of t to be 1 is 1 divided by s. Similarly, if the function f of t was 0, then Laplace transformation of 0 is equal to 0. Laplace transformation of the function e power at. We very well know that the Laplace transform is defined as Laplace of f of t is equal to integral 0 to infinity e power minus st f of t dt. Here in this problem, the function f of t is e power at. So we write Laplace of e power at is equal to integral 0 to infinity e power minus st e power at dt, which is equal to integral 0 to infinity e to the power of minus s minus at dt. When integrated, we get e power minus sat divided by minus of s minus a, where t varies from 0 to infinity. This limit exists if s minus a is greater than 0 as t is greater than 0. So when we apply upper limit minus lower limit, we get 1 divided by minus of s minus a into e power minus infinitive minus e power 0 to be equal to 1 divided by minus of s minus a into 0 minus 1, which when further simplified gives us 1 divided by s minus a if s is greater than a. Therefore, we have now proven that Laplace of e power at is equal to 1 divided by s minus a if s is greater than a. Similarly, we can also derive the Laplace transformation of e power minus at to be equal to 1 divided by s plus a if s is greater than minus a. Next, we look into another example where Laplace of sin at is equal to a divided by s square plus a square for s to be greater than 0. We know what the Laplace definition is. To the function f of t, we substitute sin at. So we get Laplace of sin at is equal to integral 0 to infinity e power minus st sin at dt. Don't you recall the formula of integral e power as sin bx dx, which is written as e power as divided by a square plus b square into a into sin bx minus b into cos bx. Here, a takes the value minus s, b is equal to a, and x takes the value t. When we substitute these to the formulae, we get Laplace of sin at to be equal to e power minus st divided by minus s the whole square plus a square into minus s sin at minus a cos at from the limit 0 to t. When we apply upper limit minus lower limit, we get 0 minus e power 0 divided by s square plus a square into 0 minus a cos 0. When simplified, we get a divided by s square plus a square if s is greater than 0. Therefore, Laplace of sin at is equal to a divided by s square plus a square if s is greater than 0. Similarly, we can find out the Laplace transform of the function cos at, which is s divided by s square plus a square if s is greater than 0. We look into the Laplace transform of the function t power n. As we know, the definition of Laplace transformation is to the function f of t, we substitute the function t power n. Here, to integrate, we go by the method of substitution. We put st to be equal to x, which implies t is equal to x by s. So when we differentiate with respect to t and x respectively, we get s into dt is equal to dx, which implies dt is equal to dx by s. So if t varies from 0 to t, then x will also vary from 0 to infinity. Now when we substitute these into the definition, we get Laplace of t power n is equal to integral 0 to infinity e power minus st x by s to the power of n dx by s. So we get 1 divided by s to the power of n plus 1 integral 0 to infinity e power minus st x power n dx. As we know the definition of gamma of n plus 1 to be integral 0 to infinity e power minus x power n dx to be nothing but n factorial. So we get 1 divided by s to the power n plus 1 gamma of n plus 1, which finally gives us n factorial divided by s power n plus 1 for every n. Therefore, we come to a conclusion that Laplace of t power n is n factorial divided by s power n plus 1 if n is greater than minus 1 and s should be greater than 0. Now, in particular case, if suppose n takes the value 1, then what would be the Laplace transformation of t? So, since we know the definition of Laplace of t power n proved as n factorial divided by s power n plus 1, in place of n when we substitute 1, we get Laplace transform of t to be equal to 1 divided by s square. Now we consolidate the table of elementary Laplace transformation. These are the 8 very elementary Laplace transformation which was derived and proven now. These are the 8 which has to be kept in our mind for the understanding of our future sections. Well, in this video, we have studied the basic of Laplace transformation, its definitions, applications, and condition for Laplace transform to exist, and also we have seen how the definition of Laplace transform could be used to derive the very elementary Laplace transformation. In the next video, we will discuss some properties of Laplace transformation. Thank you for watching this video.